I'm at Oak Ridge National Labs, and I'm in the discrete algorithms group there. And I wanted to talk a little bit about um, implementing graph algorithms on neuromorphic hardware. So yeah, so a little bit of my background. I'm a graph theorist by training. So I got my PhD in just like pure mathematics. And when I got to Oak Ridge National Lab, I found Katie Schumann and Prasanna Date and Kathleen Hamilton, and we've done some neuromorphic work since I've been there. So I just wanted to say that this is going to be sort of from a graph theory perspective. So I think everybody knows what a graph is. I just wanted to establish the sort of notation. V is my vertex set, E is my edge set, and I'm a vertices and edges person, but sometimes I'll say nodes as well, just to and also I very much like this embedding of the Peterson graph. So I like to have an excuse to show it to everybody in the slides, but just to establish a little bit of notation. So the thing I like about graph theory is that it's incredibly applicable, right? There's all sorts of models that you can make to model sort of real world phenomena, and there are all sorts of graph algorithms you can run on these models to tell you something about, sort of real systems in the real world. So the one I want to sort of highlight here, or maybe just sort of keep in everybody's mind, is that HPC, high performance computing network topologies, are graphs, and there's all sorts of graph algorithms running sort of under the hood in supercomputers. And we're going to come back to that later. I just wanted to sort of give a little overview slide of things that graphs can do, or things that you can do with graphs. Rather, you can, in a social network, large cliques are large friend groups. You can find vulnerabilities in electrical networks. Google's PageRank algorithm, for example, is one big graph algorithm. And I just wanted to mention the sort of shortest path problem because we're going to focus on that, implementing that on neuromorphic hardware. I also wanted to just kind of say that I'm coming at this from the perspective of I don't have any sort of set neuromorphic system in mind when I talk about neuromorphic things. I sort of think of neuromorphic computing being done on some sort of a platonic ideal machine. So it's like thinking of traditional computing done on a Turing machine or something like this. So at times I might talk about some functionalities that are either hard to implement or are not implementable on sort of neuromorphic hardware that exists, today. I have a fellow researcher at Oak Ridge, Parker Mitchell, if you know him, and he'll sometimes call me and say, "Hey, I'm working on this new chip. What's something you would like it to do to sort of implement these graph algorithms?" So I guess I would also like to sort of highlight that I might talk about some things that are you can't really do them yet, or they're maybe difficult to do, but I hope in the future there will be some new hardware tweaks that allow us to do sort of anything we want on neuromorphic chips, right? So the idea, loosely speaking, is neuromorphic systems sit on top of a directed graph. We all know lots of applications for neuromorphic systems. They should be maybe a good place to sort of compute some graph algorithm things. And by this, I mean, you spike some you set up your neuromorphic system the way that you want it. You spike some neurons, you let it run for a while. Maybe you pause the activity, maybe you change some parameters. and then you spike some things again, and you look at your collection of spike rasters, and you determine something about the graph. So it's not like a control problem or a learning task or anything like this. It's you know, you do something to the neuromorphic system and you learn something about the graph. So you somehow compute a graph algorithm inside of this neuromorphic system. And I should say that there are definitely ways to be clever about it. The graph, the neuromorphic system that you're computing on does not need to be basically the exact direct embedding of the graph you want to know something about. You can get cute, you can build gadgets, you can do sort of more complicated things. In this talk, we always do just sort of a direct embedding. So we've got a graph that we want to know something about. We embed it into a neuromorphic architecture where the directed edges are synapses, the nodes are precisely the neurons. We tune the parameters to whatever we need for our application, and go from there. So it's very much of interest what sort of things you can do as sort of indirect embedding, and that's sort of a future sort of direction. So I wanted to give you some quick examples. So the longest, shortest path in a graph. So let's say starting at a node, you want to find the longest path between it and some other node, so that the minimum distance between the two of them is as long as possible. It's a fairly standard, problem. It actually has all sorts of applications in natural language processing and routing and all of this. In this graph, if you started at 0, the furthest away you can get is 6. So that's 0 to 3 to 2 to 5 to 6. And you can iterate over all pairs to find the sort of all pairs longest, shortest path. This was studied previously by Kathleen Hamilton, Tiffany Mintz, and Katie Schumann. And what they showed was that if you spike sort of a source neuron and let the system, and every time a neuron spikes, you set the refractory period to infinity or larger than the graph or what have you. So each neuron spikes only once. When you look at the spike raster, what you can extract between two nodes is a subgraph that contains all of the longest, shortest paths between the two of them. But in this sort of very degenerate case, for example, you see that the subgraph that contains all the longest, shortest paths from S to T is the whole graph, right? So this is not ideal. So what we did, this is just sort of a little hack. This is also the sort of first thing that we don't know an actual practical implementation of. You can sort of tweak it so that no two neurons fire at the same time. So ties are broken, but if 3 neurons were going to fire at time step 5, they'll all fire between time steps 5 and 6. Because you add just sort of this little fractional offset weight. The weights are all distinct. No two paths have sort of the same offset weight accumulated, but it never adds up to more than 1. So we just implemented a break ties thing. I'm going to go a little bit quick here. I'm running out of time, I think. So we can also implement Prim's algorithm for finding minimum spanning trees. This is a greedy algorithm. By taking a neuron, spiking it, the first thing that spikes, you stop neuromorphic activity and you grab those two, and then you spike them. And the first thing that spikes that wasn't already in the tree, you grab it and you restart and you spike all 3 things. And so at every step, you sort of grab the thing that's the closest to the tree that doesn't create a cycle. And we can do this neuromorphically, actually, and we've implemented it and done some benchmarking on that. And I guess I'll skip the Ford Fulkerson, but I want to say every algorithm that we've implemented is either based on breadth first search or is a greedy algorithm. And we think these are good places to look for graph algorithms that you can sort of implement neuromorphically. And I guess just all of this is to say that the hope is that in the future we can sort of do some more complicated algorithms that maybe take shoulder some of the burden under the hood of a high performance computing system. There's a lot of message passing, a lot of routing, a lot of sorting that goes on in HPC, and energy is very expensive when you're using a supercomputer. So the hope is that maybe a neuromorphic coprocessor can handle some of these graph algorithms and save some money on your electric bill. And that's really the sort of purpose. So.